Today we're going to look at the period of a mass on a spring that's oscillating. Okay, so this simulation shows two different amplitudes. All right, we'll watch it again. And we can see that clearly, even though the one on the right appears to be going faster, the period is the same. All right, next we're going to look at mass. So spring 1 has 250 grams, while spring 2 has 100 grams. All right, again, I'll play this one more time. And we can see that clearly spring 1 takes longer to go up and down than spring 2. All right, here, spring 3 is a spring with a stiffer spring constant. It's harder to move it. So this one's a little harder to see, but spring 3 definitely goes faster. One more time on that one. All right, now this one we're going to do on the Earth first. All right, and then we're going to reset it to the moon. And then I'll time it. And then we're going to turn gravity off altogether. All right, and so we got 0.6, 0.63, and 0.61. So it didn't seem to matter whether I was on the Earth, the moon, or had no gravity at all. All right, and now you have to consider that there was human reaction time in that, but overall, the differences were so small that we can say that the acceleration due to gravity actually doesn't affect the period of a mass on a spring, even when it's hung vertically and gravity is acting on that mass. So, the only two things that affected the period of a mass on a spring were the amount of mass and the spring constant. So here's the equation, and it works for either a horizontal or a vertical spring. All right, capital T for period. All right, and instead of a subscript P for pendulum, now we have S for spring. All right, and that equals 2 pi times the square root of the quantity m over k. M is the mass and k is the spring constant. So what happens if we don't ignore that friction or air resistance? We're not going to talk about this too much in this class, but I want you to see what it looks like. So that's when you get what we call damped harmonic motion, or a damped harmonic oscillator, all right, where it keeps oscillating, but the amplitude decays over time. The period actually remains the same as long as the mass and the spring constant stay unchanged. So this is what a graph of position versus time would look like. Okay, so we're going to do a little bit of a comparison between a pendulum and a mass on a spring. These are the only two simple harmonic oscillators that we're going to look at in this unit. So a pendulum, the period depends on length and gravity. And the amplitude is measured in degrees. Remember, it must be less than 15 degrees to be considered simple harmonic motion. Mass on a spring, the period depends on the mass and the spring constant, and the amplitude is measured in meters. So for each one of these, there's something physical about the system, all right? The length of the pendulum or the stretchiness of the spring. So then you just have to remember that gravity matters for a pendulum, all right, but the mass doesn't matter, whereas the mass on a spring is the opposite. Okay, it depends on the mass, it's right there in the phrase, but it doesn't depend on gravity. In fact, we could turn it all the way off. So here's a cutout from the equation sheet you'll get on the AP exam. So the first equation here all right, talks about the period. But the stuff in the middle, well, I don't know what that W thing is. So we're going to ignore it. We'll get to it later. Next unit, in fact. Okay? But there's that equation I told you you'd get. The period is the inverse of the frequency. All right? And then you have the equation for a spring and the equation for a pendulum. All right? These are the only three equations that deal with simple harmonic motion that are on your equation sheet.